Well, hello physics students. This is Mrs. Bauer. I hope you guys are having a great day, and we're just going to review a little bit of the trigonometry that we covered last class to give us a heads up of what we're going to do next. So turn to page 13 in your balanced force particle model packets, and you should see this page right here. And some of you have these problems done, some of you do not. So let's just review some of these problems. We'll do the evens, 8, 10, and 12 today. So problem number 8. Why don't you guys go ahead and take a few minutes to review problem number 8 with the people next to you, and if you have not tried it, take this time to try it on your own. So why don't you pause the recording now, and in just a couple minutes unpause it and we'll work it out together. Okay, so this is problem number 8. Let's write that. Problem number 8. And so first thing, when you want to solve for this type of problem, we have to identify which sides of the triangle are, well, first of all the triangles that you will get from me are right triangles, or can be made to in the vein of right triangles, and we'll talk about that in just a little bit. So if this is the angle of interest, usually we call it a Greek letter. Today we will use theta. The hypotenuse is the diagonal, or the longest side, and the other leg that is touching the angle that you are interested in is always the adjacent. And then the one that's opposite the triangle right here will be opposite. Okay, so since we're interested in this angle and we are given the adjacent and the hypotenuse, which trig function covers the adjacent and the hypotenuse and the angle? I hope you said cosine. Cosine theta is equal to adjacent over hypotenuse. Okay, remember that cosine theta goes together. Cosine doesn't mean anything by itself without this angle right here attached to it. So we have cosine theta, because we don't know theta, equals adjacent, which is 12, over our hypotenuse, which is 15. Okay, now to get theta out by itself, because remember it's attached to this cosine, what must we do? That's right, take the inverse cosine. So it's cosine negative 1, and you take what's on the other side of the equal sign, bring it in, so 12 over 15, and this is going to be equal to theta. And then you just put that in your calculator, and I need to grab my calculator. Okay. So for those of you who are coming from math class that you're working in radian mode, make sure that you go to mode and you are in degrees for physics. So we are in degrees. That's great. I'll quit that and we'll do second cosine. Make sure you use parentheses. 12 divided by 15. And I got 36.8. So theta is equal to 36.8 degrees. Alright. So let's go down to problem 10. Problem 10, we were looking for that angle right there. Oh, I copied problem 9. Okay, we'll do problem 9. Problem 9, we are looking for this angle. Now, take a look at problem number 9. The hypotenuse right here is 134 meters, and this side is labeled as 1 meter. Now, do you think that this triangle is drawn to scale. If this is 134 meters, you would think if a side were to be labeled 1 meter, probably would be this side right here. This side is labeled 1 meter. So it's always good to kind of look at your pictures and say, do these numbers make sense? So then when you get an answer, you're not thrown off by that answer. Okay, so again, this is the adjacent side because it's touching, it's the side that's the other side touching the angle, that's not the hypotenuse. So this is kind of redundant, but it's another cosine. So cosine theta is equal to adjacent 1 over 134. To get theta all by itself, we have to do cosine inverse 1 divided by 134. Okay. So then we do inverse cosine 1 divided by 134, and we get 89.57. degrees. Very close to 90. So let's think about this. If this is 134, the triangle's probably going to look even more exaggerated than this. This side is going to be really, really tiny, W1, and this side is going to be really, really long, 134. And this side would be almost just as long as the hypotenuse. So it's going to be a really, really skinny, long triangle. And so this is going to be very close to 90, which it is. So that does make sense. Cool. All right. Let's go to that airplane problem. I think that was number 12. Okay. So let's look at this together. So we have a plane going this way, and the wind is blowing this way. So the plane, you can imagine, we are going to draw this. Let's get okay, so you can imagine that the plane is, if there was no wind, the plane would just travel along this trajectory as shown. But there is wind, so the plane is going to travel. That is a really bad. Try this again. Okay. So the plane is going to travel. Well, it's supposed to be a straight line, folks. Sorry. Okay, there we go. The plane is going to travel that way. This arrow is a vector, and remember, vectors have magnitude and direction, but not a place. So I could take this arrow and bring it over here, like so. So this is 22 meters per second. So remember that when we add vectors, we add them head to tail. And the total goes from where we start right here to where we end right here. So the total velocity relative to the ground, this is what we're looking for. The angle of deviation in the flight plan is this one right there. Okay, so to solve for x, that's relatively simple because we can just use Pythagorean theorem. Let's go ahead and do that. So we do a squared plus b squared equals c squared, and so a is 90 plus b squared 22 equals c squared, and so you solve for that, plus 22 squared, something that's 92.6. And then you have to look at, this is in meters per second, this is in meters per second, so this will be meters per second. So the wind is actually making the plane go a little faster than what the engines are doing by itself. Angle of deviation, so we have, so this is the hypotenuse right here. Here's our angle, so this is our adjacent, and this is our opposite. Which trig function uses adjacent and opposite? That's right. Ooh, I don't want that. Like this. Change the color. Blue. Okay. Shoot. There we go. Okay, so we want to find the angle, so tangent. Theta is equal to opposite over adjacent. So tangent theta is equal to opposite, which is 22, over adjacent, which is 90. To get theta all by itself, we have to do inverse tangent. 22 divided by 90 equals theta. And let's put that into our calculators. $13.7. So I got 13.7 degrees. There we go. Okay. So let's put that into our book file. Close this up. Alright. Go there and page. Okay. So now what I want you guys to do is I want you to turn to page 18 in your packet. It looks like this. We have a sign of sorts. So here's our sign. There's our sign right here. And it's being held up by two ropes across like a corner of a room. So we have rope 1 and rope 2. First thing we're asked to do is to sketch a free body diagram of the sign. The second thing to do is to draw a system schema, which is already drawn for us, so you don't have to do this one. Skip today. Okay. And the last thing is qualitative vector addition diagram. Hang on to that for a second. We're not going to do that quite yet. But so first thing I want you to do is draw a free body diagram. And then we will go ahead and solve for things. Okay, so pause this now, take a minute after you draw your free body diagram, and then unpause it. Okay, welcome back. So, free body diagrams are pretty simple for things with ropes because it looks almost just like the picture. We always have our weight of the sign going down, so weight by the earth on the sign. We have rope 1 pulling this way, and, rope 2 pulling that way, and rope 1 pulling this way. So ropes have tension, so it's the tension by 2 on the sign. This will be the tension by 1 on the side. Okay, so that's a free body diagram. Sketch the vector addition diagram. Now, remember that our vector addition diagram, we have to add vectors head to tail. Add vectors head to tail. And over here, a free body diagram, all tails of the vectors are on the dot. So, for a free body diagram, we draw all the tails on the dot. For a vector addition diagram, we don't. So let's start with the weight. So we start with the weight. It's cricket. So this is our weight. And then tension 2 goes that way, and tension 1 goes that way. Now notice, the sign isn't moving. So what's that special word that we use when things are not moving and all the forces cancel out? It starts with an E. Good, equilibrium. Okay, so if we're in equilibrium, it means that all the forces, so the sum of the forces has to equal 0 newtons, which means that if we start here and we add up all our forces, we have to end up where we started. So this is our vector addition diagram. So it shows that the sum of our forces is 0. It doesn't matter the order in which we add them. We can add them. Let's say we go T1 plus T2, T1 plus weight plus T2. So T1 plus the weight plus T2. That works. Or we could do T1 plus T2 plus the weight. And as long as we get back to where we started, we're good. So it doesn't matter which way you decided to add them. What matters is that we added them. Okay, so let's put this in our number pile. Close this. So, okay, does your system schema have, okay, in your free body diagram, did you represent the system with a particle? Yes, so that's our dot. Is it obvious when you intended two forces to be equal that you intended one force to be greater than another? Pretty much. And did you label your forces with the object exerting the force in parentheses? Yes, we did with our, not in parentheses, but with our subscripts. And did you add vectors head to tail? Yes, we talked about this. On the graph below, draw the vector addition diagram to a precise scale. Be sure to write down your scale. So we can skip this because we talked about this above. But what I want to do is, let's solve, in the bottom part right here, let's solve for the tensions 1 and 2 of the ropes. And I'll show you how to do this. So I'm going to redraw our free body diagram down here. So we have our weight. We have T2, and our weight is 1, 2, 3, 4, 5, 6, 7 squares down. So we're going to go 7 squares up because we have to make it cancel out. 1, 3, 4, 5, 6, 7. And then T1, see T2 goes over 1, 2, 3, 4, 5, 6. So I'm going to make T1 go over 6. 1, 2, 5, 6. Okay, so I'm going to sort of okay. Now, we were told that this is 5 kilograms. We haven't learned yet how to change kilograms, well, how to get a mass, kilograms, to weight, newtons. But I will tell you right now that this is 50 newtons, and we will discuss that when we get back, how to go from grams to newtons. Okay, so this is 50 newtons. Okay, and we were told that the pitcher, this work? The picture, the angle, the vertical angle is 25 degrees. So let's go back to this one. So this angle right there, so it's a different color. This vertical angle is 25 degrees. They actually give us something right here. That's opposite of 10, so we're good. Okay, so we look. We know that this weight has to equal, call it T1y, and this would be T1x. It's much easier to deal with the components of our vector, which is what we were talking about when we were doing all the triangles before, than dealing with the diagonal. So if we look at just the verticals, our ups and downs have to cancel out. So if our weight is 50 newtons, we know that T1y now will have to be 50 newtons. Excellent. So now, with this side, which happens to be our adjacent, and with this angle, we can find our opposite. So we have adjacent and opposite, so that would be tangent. So tangent theta is equal to opposite divided by adjacent. I want you guys all to start writing the equation down and then plugging in numbers. If you go ahead and just do it straight on your calculator and somehow you make a mistake or you learn radian mode, I have no way of knowing when I'm looking at your work what possibly could have gone wrong. If you show your work, I can see if it's a big mistake or a little mistake, and that'll help you get partial credit. If it's wrong with no work, you just won't get any credit. So this way, it helps you and helps me to see what's going on. So, tangent, 25 degrees. Opposite is T1x. And adjacent is 50. And so then to solve for T1x, we multiply both sides of the equation by 50. So then we have 50 tangent 25 degrees is equal to T1x. And this is equal to so this is, if this left side is 23.3, that means the right side is 23.3. So now we have T2. To solve for T1, we have the legs of the triangle, so let's get the hypotenuse. So a squared plus b squared equals c squared. A is 50 plus b is 20 equals c squared. So solving for c squared, or c actually. C is equal to 50 newtons. So that means that T1 is 55 newtons. Okay, so if we go back up to the picture, let's see if that makes sense. This row 1 is probably holding up more of the weight of the sign than row 2, which is just off to the side. It's just pulling it over. So this row 2 is holding about half the tension as row 1. And that makes sense. It makes sense in the picture, it makes sense of what we got. So yay! Perfect, we are all done with this part. The next thing I want you guys to do is to look on page 19, the next page, and try to solve this problem. So take at least 10 minutes with the people around you to solve this problem. Okay, pause it and then you can start in just a little bit. Okay, welcome back. So, a volcanologist needs a lava sample from the active lava below a plateau inside a volcano. So we have this diagram here. We have two anchored ends. They're each each 39 degrees. So three-body diagram is going to look very similar to this. So we have the tension in the cable, which we're given as 125 newtons, and then we'll call this tension 1 and 2. And again, we will find our components of this. We look at always the components. If something's at an angle, you always go to the components. This is 38 degrees, and over here this is 38 degrees. Okay, so if this is 125, and we have two vertical sides. We have two vertical sides. We have this side and this side. And since these are equal triangles, each vertical side is going to hold up half of this total weight going down. So 125 divided by 2. 62.5. Okay, so now we need the horizontals, but look over here. We have an angle, we have an opposite side, and we'll need the adjacent. Actually, we don't really need the adjacent because we're really concerned in the tension. So let's look at just T2. We want T2, so this is a hypotenuse and opposite. So we use sine theta is equal to opposite over hypotenuse. Okay, so sine theta is equal to opposite over hypotenuse. So sine 38 degrees is equal to opposite 62.5 divided by the hypotenuse. Now be careful because the hypotenuse is in the denominator here. So the thing that you want to do is multiply both sides of the equation by the hypotenuse first to get it up on top. So we have the hypotenuse times sine 38 degrees, and remember this all goes together, equals 62.5. Now you can divide both sides by the sine 38, which is sine 38 degrees, cancels out here, so that H sine 38. H is equal to 62.5 divided by sine 38. So H, the hypotenuse, is equal to 101.5. So that's the attention in each row. Okay, so we will work on this more. Expect a quiz next class on just triangles, so you have to be able to find the sides of a triangle and the angles. Work on the additional problems on page 12 and 13 of this packet. You can go in for help at lunch. Mr. Keating and Miss Holyfield are available in room 230 at lunch every day this week, except Friday. So I hope you guys have a wonderful day, and I will see you next week. Take care.